Matrix multiplication is complicated. Instead of matrix multiplication, maybe there's an easier alternative, such as multiplying by a scalar. In fact, there is. As a concrete example, the matrix 5, -7, 1, -3 multiplied to the column vector 1, 1 gives the product -2, -2. We can get the same product by multiplying the scalar -2 to the column vector 1, 1. Although this trick does not happen all the time. When it does work, we have special names for these things. The scalar is called an eigenvalue, and the vector is called an eigenvector. This lesson is about how to find eigenvalues and eigenvectors when given matrices. We find eigenvalues, symbolized as the Greek letter lambda, by solving the characteristic equation, which is the determinant of a minus lambda I. We set that equal to 0. A minus lambda I essentially means we're going to subtract this eigenvalue, which we don't know yet, lambda, from all the entries along the main diagonal of a matrix A. Then we find the determinant and set the determinant equal to 0 and solve for lambda as our eigenvalues. An equivalent version of the characteristic equation has lambda I minus A instead of A minus lambda I. Whether we go A minus lambda I or lambda I minus A, it's personal preference. I was taught to go A minus lambda I, so I use that by habit. Having solved for eigenvalues, next we go on to find eigenvectors, symbolized as the letter V, sometimes as the letter P. We substitute these eigenvalues into the homogeneous system of equations. Notice that the coefficient side, we have A minus lambda I again. We're subtracting these eigenvalues from the main diagonal of matrix A. This homogeneous system of equations will have infinite solutions, and the solution set in vector form will be our eigenvectors. An equivalent way of expressing the homogeneous system is to have the coefficients as lambda I minus A. Another way of calling an eigenvector is a basis of an eigenspace for a certain eigenvalue. Let's go find some eigenvalues and eigenvectors. Find the eigenvalues and the eigenvectors of the matrix A. Eigenvalues, symbolized as lambda, are found by solving this characteristic equation, the determinant of A minus lambda I such that it is 0. In other words, eigenvalues make this determinant equal to 0. A minus lambda I means we're going to subtract lambda from all the entries along the main diagonal of this matrix A. 5 minus lambda, -3 minus lambda, and the -7 and the 1 stays as is. And we get the determinant of this. It's a simple 2x2 determinant, AD minus BC. 5 minus lambda times -3 minus lambda minus -7 times 1. Expand everything and simplify. The 5 times -3 is a -15. -5 lambda. Negative lambda times -3 is 3 lambda. Negative lambda times negative lambda is a positive lambda squared. And we subtract a -7 times 1, which is +7. Collecting the like terms together, we have lambda squared minus 2 lambda minus 8. And we factor this polynomial. Think of two numbers that multiply together to give -8 and added together to give -2. Lambda minus 4, lambda plus 2. This is the characteristic polynomial. And when we set it equal to 0, it's a characteristic equation. The eigenvalues are the roots, or the solutions, of this characteristic equation. To make this polynomial equal to 0, lambda has to be -2 or 4, and these are our eigenvalues. Then we find the eigenvectors by substituting the eigenvalues into A minus lambda I and solving the homogeneous equation. Recall that homogeneous means that the answers to the system of equations is all equal to 0. It doesn't matter which eigenvalue we begin with, just pick one. Let's say lambda equals -2, and we find the eigenvectors for this particular eigenvalue. A minus lambda I, which means we're going to subtract lambda from all the entries along the main diagonal of A. But in this case, lambda is -2. Because we're solving a homogeneous system, augment a column of zeros to this coefficient matrix. Simplifying, 5 minus a -2 is a +7, -7, 1, and -3 minus a -2, think of it as -3 plus 2 is -1. And we just keep solving this as we would any system of equations. Try to get as many zeros as we can. We can go 7 times row 3 minus row 1 to get rid of those 1 and negative 1. Then multiply row 1 by 1 over 7 to get a leading 1. We have now solved the system. Notice that on the coefficient side of this augmented matrix, we don't have a leading 1 for x2. So then x2 is going to be our parameter, let's call it t. And we solve for x1. x1 minus x2 equals 0. Therefore x1 equals x2, and x2 being t, x1 is equal to t. Our solution set looks something like this. x1, x2, both of them being equal to t, we can factor out that t to get the column vector 1, 1. This is our eigenvector corresponding to the eigenvalue lambda equals -2. Let's work on the other eigenvalue now, lambda equals 4. Similarly, we go a minus lambda I. We're going to subtract lambda equals 4 from all the entries along the main diagonal of a. 5 minus 4 and -3 minus 4. Simplifying, on the coefficient side we have 1, -7, and also 1, -7. And the matrix is augmented to a column vector of zeros. Row reducing the matrix, we can go row 3 minus row 1. We see that we do not have a leading 1 for x2. So then we let x2 equal to our parameter. Let's call it r this time. x1 minus 7x2 equals to 0, so then x1 equals 7x2. x2 being r, x1 is 7r. The solution set is therefore x1 equals 7r, x2 equals r. We can factor out the r to get 7, 1, which is the eigenvector for this eigenvalue lambda equals 4. Let's summarize what we just found and also introduce some new vocabulary. The eigenvalue -2 has an algebraic multiplicity of 1, because lambda equals -2 only comes up once in our characteristic equation. From this eigenvalue, we only have a single eigenvector, and therefore lambda equals -2 has a geometric multiplicity of 1. The next eigenvalue, lambda equals 4, also appears once in the characteristic equation, so it has an algebraic multiplicity of 1. And from this eigenvalue, we only have one single eigenvector, therefore lambda equals 4 has a geometric multiplicity of 1. Though not necessary, we can check our work to see if matrix A multiplied by an eigenvector does in fact equal to an eigenvalue multiplied by the eigenvector. Starting with the eigenvalue -2. On the left side, matrix A multiplied by the eigenvector 1, 1. And on the right side, we have the eigenvalue -2 multiplied by the eigenvector 1, 1. Doing matrix multiplication, we have 5, -7 multiplied by 1, 1, and we add the result, -2. And then 1, -3 multiplied by 1, 1, then add the products together, -2. On the right side is easy, -2 times 1, -2 times 1, and yes, in fact, we do have left-hand side equals right-hand side. For the eigenvalue, 4, matrix A multiplied by the eigenvector 7, 1 is on the left-hand side, and on the right-hand side we have the eigenvalue 4 multiplied by the eigenvector 7, 1. Doing matrix multiplication, we have 5, -7 multiplied by 7, 1. We have 28. And 1, -3 multiplied by 7, 1. We have 4. On the right-hand side, 4 times 7, 4 times 1, we also have 28, 4. Therefore, we're able to verify our answers. In fact, we have found the eigenvalues and eigenvectors of this matrix A. Eigenvalue eigenvector questions can be complicated because there are so many steps involved. It often helps to work through a few of these examples together. Find the eigenvalues and eigenvectors of the matrix B. Just like before, we find eigenvalues by solving their characteristic equation. We subtract lambda from the main diagonal entries of matrix B, get the determinant, and set the determinant equal to 0. Then solve for the eigenvalues lambda. This is a 2 by 2 determinant, AD minus BC, 8 minus lambda times 8 minus lambda minus 9 times 0. The 9 times 0 is just 0. Setting the determinant equal to 0, the root of this equation is lambda equals 8. In fact, it's twice. We have two of these 8 minus lambda factors, so we have lambda equals 8 twice. This means that this eigenvalue 8 has an algebraic multiplicity of 2. Next, we find eigenvectors by substituting lambda equals 8 into the homogeneous system of equations and solve the system. On the coefficient side, we have 8 minus lambda along the main diagonal. Since this is a homogeneous system, we augment the coefficient matrix to a column of zeros. Simplifying, lambda being 8, 8 minus 8 is 0. Row reducing the augmented matrix, we can multiply the first row by 1 over 9. We have a leading 1 in the x2 position, which means that x2 is equal to 0. We don't have a leading 1 for x1. Let's assign a parameter, t, to x1. The solution set in vector form looks like this. x1 is t, x2 is 0. Factoring out t, we have the vector 1, 0, which is our eigenvector. Since we only have a single eigenvector associated with this eigenvalue lambda equals 8, this eigenvalue has a geometric multiplicity of 1. To summarize, this matrix B has an eigenvalue of 8, whose algebraic multiplicity is 2 because lambda equals 8 comes up twice as the root of the characteristic equation. However, we're only able to get a single eigenvector from this eigenvalue, so this eigenvalue has a geometric multiplicity of 1. Let's do a more challenging example with a 3x3 matrix. Find the eigenvalues and eigenvectors of the matrix C. Find eigenvalues by solving the characteristic equation. Subtract lambda from the main diagonal of matrix C, and take the determinant. Row 2 has the most zeros. Let's do cofactor expansion along row 2. We have 1 minus lambda, then cross off the row and column that has this entry, and get the determinant. It's a 2x2 determinant, AD minus BC, 3 minus lambda times negative 3 minus lambda minus 4 times negative 2. Expand everything and simplify. The 1 minus lambda can just stay aside for now. 3 times negative 3, negative 9. 3 times negative lambda is a negative 3 lambda. Negative lambda times negative 3 is a positive 3 lambda. Negative lambda times negative lambda is a positive lambda squared. And then we have a minus 4 times negative 2, which becomes a plus 8. The minus 9 and the plus 8 become a minus 1. The negative 3 lambda and positive 3 lambda cancel. The determinant is 1 minus lambda, the whole thing, times lambda squared minus 1. And we set this determinant equal to 0 to find the eigenvalues. The solutions are lambda equals negative 1 and positive 1. Lambda equals negative 1 only comes up once, therefore this root has an algebraic multiplicity of 1. But notice that lambda equals positive 1 comes up twice. This eigenvalue has an algebraic multiplicity of 2. We find the corresponding eigenvectors by substituting these eigenvalues into the homogeneous system of equations and solving. C minus lambda I means we're going to subtract lambda from all the entries along the main diagonal of matrix C. And this coefficient matrix is augmented to a column of zeros, as this is a homogeneous system, and simplify this augmented matrix. Then solve the system by row reduction. Looking at the 4 and negative 2, we can get rid of the 4 by going row 1 plus 2 times row 3. We can get rid of the 2 in row 1 by subtracting the 2 in row 2. We can get rid of the 2 in row 3 by going row 3 minus row 2. Turn those 2's into 1's by multiplying row 2 by 1 over 2 and row 3 by negative 1 over 2. Put that row of zeros at the very bottom of the matrix. Row 1 switch with row 3. We have our solution. We don't have a leading 1 in the third column corresponding to x3. Therefore, x3 will be our parameter. Let x3 equal to t. Row 1 says x1 plus x3 equals 0. Rearranging for x1, x1 equals negative x3. Since x3 is t, x1 equals negative t. And x2 is equal to 0. Our solution set is, in vector form, x1 equals negative t, x2 equals 0, and x3 equals t. Factoring out t, we have the vector negative 1, 0, 1, which is our eigenvector for the eigenvalue lambda equals negative 1. Now for the other eigenvalue lambda equals 1, we do something similar. We subtract lambda equals 1 from all the entries along the main diagonal of C. This is the coefficient matrix that's augmented to a column of zeros. Row 1 is 2, negative 2, 4. and row 3 is -2, 2, and -4. We can get rid of one of those rows by addition because they are just plus and minus versions of each other. Row 3 plus row 1. We can simplify that row by dividing the entries by 2, half row 1. We do not have a leading 1 in column 2 corresponding to x2 or column 3 corresponding to x3. Let's use some parameters. Let x2 equal to r and x3 equal to s. The matrix tells us x1 minus x2 plus 2x3 equals 0. Solving for x1, we have x2 minus 2x3, or r minus 2s. The solution set in vector form is x1 equals r minus 2s, x2 equals r, and x3 equals s, which can be expressed as r multiplied by the vector 1, 1, 0, plus s multiplied by the vector -2, 0, 1. Interestingly enough, we get 2 eigenvectors from this eigenvalue, a geometric multiplicity of 2. To summarize, the eigenvalue -1 only appears once as the root of the characteristic equation, and therefore has the algebraic multiplicity of 1. We only get one single eigenvector from this eigenvalue, -1, 0, 1, and therefore this eigenvalue has a geometric multiplicity of 1. The other eigenvalue, 1, has an algebraic multiplicity of 2 because 1 came up twice as the root of the characteristic equation. Moreover, we get 2 eigenvectors, 1, 1, 0 and -2, 0, 1 from this eigenvalue, which means the eigenvalue has a geometric multiplicity of 2. Find the bases of the eigenspaces of the matrix. This is just another way of saying find the eigenvalues and eigenvectors. We find the eigenvalues by solving the characteristic equation. Subtract lambda from all the entries along the main diagonal of matrix D. Find the determinant and set the determinant equal to 0. Find the values of lambda. D minus lambda I gives a 3 by 3 determinant. Row 1 has the most zeros. Let's do cofactor expansion along row 1. 3 minus lambda, then cross off the row and column and get the determinant of that. This 2 by 2 determinant, AD minus BC, is 2 minus lambda times 1 minus lambda, then minus 2 times 1. Expand everything. 2 times 1 is 2. 2 times negative lambda times 1, then negative lambda times negative lambda, which is plus lambda squared, and subtract 2. The plus 2 and the minus 2 cancel. We can collect that negative lambda and a negative 2 lambda together. Simplifying, we have 3 minus lambda as a factor, multiplied to lambda squared minus 3 lambda. We can factor out a lambda to get 3 minus lambda, then lambda times by lambda minus 3. Notice that we have these lambda minus 3 and 3 minus lambda, which give a root of 3. In fact, 2 of these factors means we have 2 of these roots, lambda equals 3. The other factor, lambda, gives a root of lambda equals 0. We can say that the eigenvalue 3 has an algebraic multiplicity of 2 because this root comes up twice. The other eigenvalue, 0, only comes up as a root once. Therefore, this eigenvalue has an algebraic multiplicity of 1. Next, find the eigenvectors by substituting these eigenvalues into this homogeneous system of equations. For the eigenvalue 0, we subtract 0 from all the entries along the main diagonal of matrix D. And we augment this coefficient matrix to a column of zeros. We solve this homogeneous system of equations by row reducing. That 3 can be made into a leading 1. Multiply the first row by a third. The 10, 2, 2 has a common factor of 2 and can be simplified. Half row 2. We can get rid of these 1s by subtracting row 2 minus row 3. And also cancel that 5 by going row 2 minus 5 times row 1. And we put that row of zeros at the very bottom of the matrix. Looking at this row-reduced form of the matrix, x1 equals 0. We do not have a leading 1 for x3, therefore let x3 be our parameter, t. Looking at the second row, x2 plus x3 equals 0. Solving for x2, x2 equals negative x3 equals negative t. The solution to this homogeneous system of equation in vector form, x1 equals 0, x2 equals negative t, and x3 equals t. Factoring out the t, we have the vector 0, negative 1, 1, which is our eigenvector associated with the eigenvalue 0. For the other eigenvalue, 3, we do something similar. Subtract 3 from all the entries along the main diagonal of the matrix D, and we augment the coefficient matrix to a column of zeros. We have a -1, +2, versus a +1 and -2. We can cancel that -1, -2 by adding row 2 plus row 3. Then 1 times 10 row 2 to get a leading 1, and we put that row of zeros at the very bottom of the matrix. Looking at the row-reduced matrix, x1 equals 0. We do not have a leading 1 for x3. Let x3 equal to a parameter, r. Then x2 minus 2x3 is 0. Solving for x2, x2 equals 2x3, or 2r. The solution set in vector form is x1 equals 0, x2 equals 2r, and x3 equals r. Factoring out the r, we have the vector 0, 2, 1, which is the eigenvector associated with the eigenvalue 3. To summarize, the eigenvalue 0 has an algebraic multiplicity of 1 because 0 only comes up once as the root of the characteristic equation. We only get one eigenvector from this eigenvalue, and therefore this eigenvalue has a geometric multiplicity of 1. The other eigenvalue, 3, has an algebraic multiplicity of 2 because 3 came up twice as the root of the characteristic equation. We get one eigenvector from this eigenvalue, 0, 2, 1, which means that this eigenvalue has a geometric multiplicity of 1. Now, to directly answer what this question is asking us to do, the eigenspace, corresponding to lambda equals 0, has the basis, which is the eigenvector, 0, -1, 1. The other eigenspace is lambda equals 3 and has its own eigenvector, 0, 2, 1, as the basis of the eigenspace.